All right. Hello, everyone. I guess we'll get started. So welcome to this guest lecture that I'm giving on web application debugging. So I guess first of all, I just want to thank Karthik for inviting me to do this guest lecture. I know he's invited me quite a few times in the past, but I've had to reject him each time, unfortunately, because of other things coming up. But this time around, it's a little bit friendlier to the schedule just because it's pre-recorded. So I'm able to give it this time around. I guess just to tell you guys a little bit about myself. So I did my PhD back in 2012 to 2016 in UBC. So I did my master's before that from 2010 to 2012 and then transitioned into PhD right after. And my advisors were Karthik and Professor Ali Mesbah. And the research that I was conducting during my PhD was basically on web application and client-side JavaScript reliability. So a couple of things that you guys should be quite familiar with, especially this first part right here, which is web applications, because this is what the course is about. And then right before I did my dissertation defense, I got into this company called SAP as a software engineer. So in this case, I was hired and I'm still working for the performance and reliability team, or the P&R team. I'm going to be talking to you guys a little bit more about stuff that we do in the team, because this is one of the central foci of this talk. But basically, just to give you sort of a gist of what we do performance detection and localization. A couple terms that you guys might not be super familiar with, but we're going to sort of clarify that a little bit more throughout the lecture. So in this team, it is a dev team. There's no testing team in our organization, or at least that particular product that we're working on. So there's a lot of development that we do. But at the same time, there's also a lot of different unknowns in sort of the tasks that we perform. And that entails us having to do some research, basically. So I'll talk a little bit more about that as well during the lecture. Just to give you a sort of a flavor of it, we actually published our first research paper this year. So it was published in this journal called STVR. All right, so as I mentioned earlier, the central focus of this talk is me telling you guys what we do in the P&R team and sort of describing some of the challenges that we face, both from a macro perspective, so sort of from a general perspective, and also from a micro perspective. So what are the specific challenges that we face with specific tasks that we do within the team? It's not necessarily the main topic or the topic that we're going to be spending the most time on, but it's what all the things that we're talking about here would lead up to, basically. Okay. So for this lecture, we're going to start off with a couple things, basically. So we're going to start by defining certain terms and concepts, just to make sure that we're all on the same page. And then after that, once we've made those definitions, we're going to sort of cast them in the context of functional debugging. And the reason why we're doing that, despite the fact that we're a performance team, is because, well, first of all, you guys are probably more familiar with functional debugging. It's what basically every software engineer, software programmers, developers do. But also, one of the other reasons is because it actually shares a lot in common with the challenges that we face with performance debugging. So there's a little bit of an overlap there. You know, it's not necessarily one-to-one. There are certain things that are unique to performance debugging, and certain things that are also unique to functional debugging, and vice versa. But there's quite a bit of overlap. So I thought it would be good to sort of give you guys an overview of this before we talk about performance debugging. All right, so this is the title that we started this entire lecture with. So it's called Web Application Debugging. Now, for the first part, web application, you guys are probably very, very familiar with this. This is the last lecture. So you guys should have a great deal of familiarity with web applications and how they work. But there's this last word right here, debugging, which is kind of vague in a certain sense. People have different conceptions of what it is. So what we're going to do now, and we're actually going to be doing this throughout the lecture as well. I'm going to be giving you guys maybe around 15 seconds or so to think about this question. So what do you think this is? What do you think debugging is? So maybe for about 15 seconds, just think of your own sort of conception of what you think debugging is based on what you know so far. And then we'll discuss it a little bit more afterwards. So I'll give you guys maybe around 15 seconds. All right. So I was just counting in my head, so hopefully that was enough time. But let me give you guys some answers that I think some of you guys might have given. Okay. So when you hear the word debugging, a lot of people probably think of it as setting breakpoints and stepping through the code. So for example, in this image right here, you have this JavaScript code. I'm pretty sure this one actually comes from my website. So you have some JavaScript code, and then you do what you regularly do when you're doing debugging, or when you're breakpointing in other languages. So you basically set a breakpoint, you execute your code, and then you wait for that breakpoint to get hit. And then you basically just step through your code and see where certain errors might be appearing. So this is probably the main thing, or one of the most common things that people would think about when they hear the word debugging, is breakpoint debugging. Okay, so another thing that you might be thinking about is putting logs inside the code. So again, in this example right here, you have this very, very simple piece of code. It could basically represent any language, but I guess with the presence of console.log, it means it's JavaScript. So in this case, you have this very simple code, and then you want to debug it. You want to know exactly whether this if branch right here gets executed. Excuse me. So in that case, one of the options that you have is put a console log. So you would put console.log and then whatever message you want to include. So in this case, if this console log appears, that means that this branch was taken. So therefore, you have a better idea of the control flow during the execution. Okay, so this is where we get the term debug logs, basically. When you're performing debugging, you put in logs to give you a better idea of what executed. Excuse me. Okay, so another potential conception that you might have is not so much breakpointing or putting logs, but maybe you're talking about figuring out where to specifically apply a certain fix. Maybe you've done breakpointing, maybe you've done logging, and you know precisely which lines of code are being affected. But it doesn't necessarily mean that you're going to be fixing it exactly on that same line of code. You might be applying the fix somewhere else. So in this little picture right here, you have someone blaming another person, basically that, the program started failing after this guy's commit. So in that case, he needs to figure out where to apply the fix, but it doesn't necessarily mean that it has to be within that same commit, right? Okay, so maybe that's another conception that you might have had. And then the last one, although I'm sure there's a few others, is maybe you're thinking of debugging in terms of finding bugs in software before we actually know they're there. So maybe in the other examples that I gave, we already know that there's a bug, and we just need to figure out exactly where that bug is coming from. But maybe you're thinking of debugging as what happens before that. So maybe you have a piece of software, you have a program, an application. You don't know how many bugs there are. You don't know what specific bugs are there, but you just want to know what bugs actually are there. So that's a type of debugging as well, because you want to eliminate the bugs in your program in a certain way. It's fair to think of it as debugging, at least. Okay. So you have these four things. So setting breakpoints, putting logs, figuring out where to apply the fix, and finding bugs in software before we know that they're there. So these are all fine. They're reasonable conceptions that you could have regarding debugging. But for the purposes of this lecture itself, we're going to be using this more precise definition. So when we talk about debugging in this lecture, we're talking about the act of detecting, localizing, and repairing functional and non-functional defects in a piece of software. Okay, so it's a bit of a mouthful. There's a lot of different terms that I'm using here, which you're probably not understanding at this point. So we're going to parse this this definition a little bit. Okay, so you guys have a better scope or better understanding of what it means. Okay. So let's start with the first three words right here. So we have detecting, localizing, and repairing. Okay. On the detection side, what we mean by detection is finding bugs in a piece of software. So, we don't know whether there's any bugs in that software. We got to detect, we got to find those bugs in there if they exist. And very likely they do exist, especially for very large programs. Okay. A couple things that people traditionally do when performing detection. So the first obvious one is software testing, especially software regression testing. So when we talk about regressions, that means you basically have one version of the program that's correct, and then you subsequently apply different commits to the program, and then later down the line, it becomes buggy. Okay, so maybe you want to figure out whether there's any regressions or bugs that have been introduced after those subsequent commits. So that's software testing. Okay, and then on the other side of it is code analysis. So instead of you having to execute your code, maybe you just want to statically analyze your code and figure out whether there's any errors in the code. So this is where stuff like linting comes in, syntax checking, which obviously compilers would come with, and on the more researchy side, symbolic execution. Okay, so that's detection. So what about localization or localizing? In this case, when we talk about localizing, we're talking about finding the root cause of a bug. Okay, just like debugging, root cause is a very vague term. So again, for this one, I'm going to be giving you guys maybe around 15 seconds again to answer this question. So in the context of localization, what do you think root cause means? You've probably heard of the term before, but what do you think it means? So I'll give you around 15 seconds. All right. So again, hopefully that's enough time. Okay, so kind of like with debugging, it's not like a simple one-word answer because there's a lot of caveats and a lot of nuances involved with defining this term. And in this particular case, it actually depends a lot on what level you're trying to debug. So for example, if you're trying to debug at the code level, the question that you'd probably ask is, what lines of code are causing certain values to be what they are at the lowest level? And when we say lines of code, we're talking about maybe individual statements. We can talk about functions. So what functions or what statements are causing a certain value to be what they are, or to be what it is? Okay, so maybe you're debugging at the code level, and in this case, the root cause would be the line of code or the lines of code. You might be localizing at the commit level. And in this case, the root cause is going to be different. It's going to be a little bit less granular. So if you're debugging or localizing at the commit level, then in that case, your root cause would be the commit. So your question would be, which commit introduced a bug? Okay. And then the third one that I've written down here is component level. So maybe you're working in a very large team, and each team is divided into different components. So one team is going to be in charge of a specific component of the software, and then another team is going to be in charge of another. And you need to figure out exactly which team to blame, right? So you have these predefined components, and maybe you're trying to just figure out exactly which component a certain bug, or which component introduced a certain bug, so that you can send it off to the correct team. Okay. So in this case, the root cause would be that predefined portion of code. Okay, so that's localization. It's basically finding the root cause, which has its own set of nuances, as we just described. And then the last one is repair, repairing. And in this case, it refers to finding the best way to apply a fix to the bug. So this one obviously assumes that you've done the detection, you know that there's a bug there, and you've also done the localization. So you have a bit of an idea of which line of code is the culprit, or which commit is the culprit. But you also need to figure out exactly how to fix the bug. Okay, so it's a little bit of a curious thing, right? Because we're basically separating these two out. Because you would think that when you're localizing, you already know what the fix is going to be. So it's a little bit weird that we're kind of separating these two. But the reason why we're doing that is because of this important note that I put in here. So what you localize is not necessarily the same as where you apply the fix. Okay, so whatever output you get from the localization step, it's not necessarily going to be the exact same input that you put into the repair step. Okay, let me give you guys a very simple example. Okay, so a little bit complicated in this slide, but just bear with me here. So let's say that you have this very, very simple program right here. So it's a very simple JavaScript function that we've implemented called compute. And the only thing that it does is it performs addition, basically. Don't ask, how come we can't just do x plus y without implementing a function? That's totally out of the point. It's beside the point. But anyways, just assume that you have this function called compute, and you have, and what it does is it basically performs addition. It returns x plus y. So let's say that the developer is working on this, and he decides that, oh, I want to add another feature, which is basically performing subtraction. Okay, so what he does is he adds all these other features. So he puts in another parameter called isSub. So if it's set to true, it performs subtraction. If it's set to false, then it performs the usual, which is addition. And then you have a couple of branches here. So it performs this computation right here if you want to do subtraction, and it performs this computation here if you want to do the addition. Okay, but in this case, let's say that the developer is not quite confident about his code yet. Maybe he wants to add a few other things later on. So he decides to set this feature toggle to false. Okay, so he basically wants this to control whether the feature is available or not. Okay. So in this case, you have this this commit, basically. And then after that, let's say that the developer finally decides that, oh, I'm confident enough about the code that I've written, so I'm going to turn this feature to true so that people can perform their subtraction now. Okay. And, he ships this one off to the customers, and the customers complain that there's a bug. They put in the values 5 and 4. 5 for x and 4 for y. And instead of returning 5 minus 4, which is 1, it returns 20 instead. Okay, so there's a bug here. Okay, but that bug doesn't exist here. That bug doesn't exist here. It only exists here, basically. Okay, so the reason why I wanted to sort of highlight this is because it clearly shows that wherever the bug is manifested, which in this case is commit to, so this is where the bug is first observed, it's not necessarily where the fix is applied, right? Because imagine if you're assuming that this is where the fix should be, all you would have to do is basically set this one to false, which doesn't make any sense, right? You're basically just turning off the feature. In this case, the first commit to manifest the bug is commit to, as I just mentioned. So that's the localization output. But the bug has actually been there since commit 1, right? So the actual fix that you want to apply is basically something that was written down in commit 1 itself, as opposed to commit 2. So you can clearly see here how what I said here, basically, what you localize is not necessarily the same as where you apply the fix. Okay, so that's one of the reasons why we basically split these two into different phases. So you have localization and repair. Right, so let's go back to those 4 things that we mentioned earlier. So those conceptions of debugging that people might have, including maybe yourselves. So the first 2, we mentioned setting breakpoints and stepping through the code, and also putting debug logs. So from the context of our definition for debugging, these ones would be classified more as debugging techniques, as opposed to debugging itself, mostly for the localization step. This one right here, so figuring out where to apply the fix. Obviously, this one refers more to the repair aspect of debugging, as we just talked about. And then this last one right here, finding bugs in software before we know that they're there. As we mentioned earlier, this one refers more to the detection side, or the detection phase of debugging. Okay. So it's, these are all related to debugging in some way, but from the context of our own definition, they're more, this one's a little bit more holistic, basically. All right, so the other side of the definition is basically this functional versus non-functional defects in a piece of software. It's actually fairly simple. I mean, it's pretty much embedded in the name itself. So for functional, the main question is, does the code actually work correctly? So you have a bunch of specifications, you have an oracle, and you need to figure out whether it's actually following those specifications. You know, is it outputting the correct value itself, for instance? Whereas for non-functional, this one doesn't refer or it doesn't pertain to a specific oracle or specification, but it's more sort of things on the side, but are nonetheless important. So for example, you can ask, does the code perform well? You know, is it taking a second to load, or is it maybe taking 10 seconds to load? It makes all the difference in the world, right? You can also ask, is it secure? You know, especially for applications like banking applications, for instance, this is a very important aspect to look into, because even if your application is working properly, if it's not secure, then you know, we have a huge problem, right? And then the other side of it is it easy to use? So are there sort of UX type of issues with the code itself? So that's the distinction between functional and non-functional. Okay, so I guess the last thing that I should note is that this is not necessarily a standard definition for debugging. And the reason why is because there isn't really a standard definition. You know, it's a very vague term that people use. But in this case, we sort of have to define it so that we have a very precise understanding and we can sort of understand each other a little bit more. Okay. And by the way, if you guys have any questions, obviously, you know, this is pre-recorded, so I won't get the chance to answer your questions live. But if you guys have any questions, please write them down and send them over to Karthik so you can forward those to me as well. All right, so we're going back to this slide again. So we have web application debugging, which is the title of the talk. We talked about debugging already. And I mentioned to you guys how familiar you guys should be with web applications. But another question you can ask is, you know, why do we care about this? You know, the stuff that we talked about when it comes to debugging, it's all very general, right? It's something that you can apply to pretty much any piece of software, any type of program. But what's so special about web applications that it warrants its own lecture, basically? Okay. So there's a couple things. The first thing that I want to highlight is that web applications are polyglots. For those of you guys who are not very familiar with this term, a polyglot basically means someone who is able to speak multiple languages. Okay, so when I say web applications are polyglots, that means web applications can speak multiple programming languages. Okay, so just for a comparison, if you look at traditional programs that are written in Java, C++, all these different languages, most of them are written in a single language. Okay. And if you're doing your traditional breakpoint debugging, for example, you would just have to do it as normal, basically. So you'd have your program, you put in a breakpoint, and then you step through the code. And your localization output is very likely going to be within that same language itself, because it's basically homogeneous, right? You're basically using the exact same language, nothing sort of cross-language happening here. So most likely it's going to be in the same language that your localization output is going to be. Okay. Whereas for web applications, it's quite different because for web apps, they're actually written almost always exclusively in multiple languages. So as you know, for client side or for the client side in web applications, you have these 3 different languages that are standard. So you have HTML, JavaScript, and CSS. And then on the server side, you also have many, many different languages that are interacting with each other. So maybe you're writing a PHP-based application. Maybe you're writing a Perl-based application. You have some Perl script. Maybe it's Node-based. And then, you know, a lot of the times people have databases in their web applications as well. So you would also need to type in some SQL. Okay, so the point here is that in maybe 99.9% of the cases of web applications, there's always going to be multiple programming languages interacting with each other. And the main implication when it comes to debugging here is that when you're doing breakpoint debugging, it's not quite as clear cut. So here, as I said, you know, if you set a breakpoint, most likely your output is going to be in the same language. But here, that's not necessarily the case, right? Maybe you're going to get a certain output, but it doesn't necessarily pertain to to sort of the root cause itself. And of course, for some languages, like for example, HTML, it might even be impossible to do breakpoint debugging because it doesn't have a control flow. Right. Just to hammer this home or this point home a little bit further, back in 2013/2017, so we wrote a couple of research papers on this. And one of our findings from that paper is that the majority of JavaScript faults are DOM related. So what that basically means is that whatever bug you have in the web application, a lot of the times they pass through DOM API functions. Okay. Obviously, this study has been, was conducted a while ago, so we're not exactly sure whether a lot of these results still apply, especially now that JavaScript has been updated extensively. But at least it goes to show how intrinsically tied web application languages are to each other, even when it comes to bugs, not just functionality, but also bugs themselves. Okay. So that was the first thing, web applications are polyglots. The other reason why web applications are so unique when it comes to debugging is because JavaScript is a very weird language. It's a very useful language, but it's also a very weird language. Okay. And the reason why I say that is because it has certain properties that make it a little bit less friendly when it comes to debugging. Okay. The first one that I mentioned here is that JavaScript is JIT compiled, or in some cases interpreted. And one of the implications of that is that syntax errors can actually make their way to production code. Just imagine having your Java code, have a bunch of syntax errors. It doesn't even make any sense in this particular case, right? So what that means is that you potentially might have to localize syntax errors for web applications. Okay. So again, for Java, for instance, or for any other traditional software or programming languages, all you have to do is basically write your code, feed it into the compiler, and your compiler is going to complain right then and there that there's a syntax error. So in this case, you're missing a semicolon. So since it's complaining, that means you're not even able to compile the code, so you're not even able to execute it to begin with. Okay. Whereas for JavaScript or web applications in general, let's say that you have these three different functions right here implemented in three different files, right? So you have show num, which calls both alert success and alert fail. Now the problem here is that there's a syntax error here in test3.js because you're missing a parenthesis, a closing parenthesis here at the end of the function definition. Now, in traditional languages, you would expect that this is just going to completely fail. Nothing's going to happen. It's going to say syntax error, right? But not so. In this case, it's actually going to succeed if lm.value is equal to 1. Because what's going to happen here is that despite the fact that test3.js is throwing a syntax error, show num doesn't know that. It only cares about what it's executing. And in this case, it's only executing alert success as opposed to alert fail. So despite the fact that there's a syntax error in one of the files that you're using, the JavaScript code is actually going to continue executing, which is kind of scary if you think about it, because you can ship with syntax errors in your code. Okay, so the other property of JavaScript that I wanted to talk about is the fact that it's untyped. So that means that you don't even have to cast variables if you want to convert it from one type to another. It's super, super loose. You can just do var x equals 1 in your declaration. And then later down the line, you can just set x to like a string or something like that. Okay. So from the standpoint of debugging, that means that data flow can be very hard to track because you have all these different types that you need to care about. It's not just one uniform type that a value can take on. Okay. So you guys are probably familiar with TypeScript, and you probably know that it tries to mitigate this to a certain extent by introducing typing. But the problem, of course, is that it's not very widely adopted as one might think it would be. And the reason is because developers still want vanilla JavaScript for its flexibility. Unfortunately, as I said here, wanting something is not necessarily the same as being able or willing to uphold that thing to its highest standards. So, just the fact that people want JavaScript because of its flexibility doesn't mean that it's able to doesn't mean that the developers are able to maintain the JavaScript code very well. Okay. So the third property is the fact that JavaScript is asynchronous. So that means you won't have just a single flow of execution that starts at the same route, but you have different flows of execution, basically. And from a debugging perspective, that's harder as well, because that means you essentially need to figure out which flow of execution you care about, which adds an additional localization step. Okay. And also in terms of reading the code, which is also important when it comes to localization. It's not just a matter of figuring out, oh, this function calls this other function, and this function also calls another function, and so on and so forth. Because in JavaScript, you have stuff like promises, XHR, worker threads, anonymous functions, all these different constructs that you won't typically find in traditional languages. Makes it harder, basically, to do the localization, because your control flow is not exactly what you would expect, as you would expect in traditional languages. Right? And I guess just to give you sort of a practical flavor of this, so this is the execution stack, or the call tree that is generated for Google's homepage. So you guys know how simple Google's homepage is. So you basically just have an image on the top that has the Google logo, and then you have a couple of input elements at the bottom. Very, very simple, but it has this very, very complicated call tree or execution stack. Okay. And then the last property is the fact that JavaScript is event-driven. Okay, so kind of like with the asynchronous property of JavaScript and how it adds an additional matrix of or an additional thing to check, basically, it's the exact same thing here. So for this one, our matrix of inputs essentially increases by another dimension, because we also need to account not just for the data that's passed in by the user, but we also need to account for the specific action that was done by the user when interacting with the application. Okay. So on the detection side, one of the main questions that you need to ask because of this event-driven property is, how do we test these interactions? It's not just a simple matter of providing a value, but you also need to provide sort of the specific action itself that's performed by the user. So how do we test that? And then on the localization and repair side, you also need to ask, how do we replicate these interactions? Because obviously, whenever you want to debug something, it's very, very important for you to actually be able to replicate the bug. Okay, so we have all those properties. So web applications are polyglots, and then JavaScript is a very weird language, but very useful one. And I talked about those properties, those 4 properties. All right, so now we're going to be going over what are some of the techniques that people use for debugging functional defects in web applications. And again, we're going to be talking about functional defects as a segue into what comes in a little bit afterwards, which is the performance debugging that we do in our team. Okay. So we're going to divide this section up into 3 different parts. So we're going to talk about detection first, and then we're going to talk about localization, and then we're going to talk about repair, similar to those 3 phases that we have for debugging. Okay. So for detecting functional defects, there's roughly 2 different categories. The first one is detecting syntax bugs. So remember, these actually matter now. For traditional applications, they usually wouldn't matter because the compiler is going to catch them immediately. Whereas for web applications, they might appear. And then the second category is detecting semantic bugs, similar to what you would usually see in traditional applications as well. All right. So on the syntax side, as I said, we don't have a traditional compiler, so we have to use something else to help us detect these syntax bugs. And by the way, the reason why I'm using the term syntax bugs is there's a very, very specific definition for what an error, a fault, and a failure is. So I didn't want to confuse you guys by using those terms interchangeably. But if I do end up using those terms, just think of them as bugs, basically. Okay. So in this case, in the absence of a traditional compiler, we can actually use something called a linter to help us detect these syntax bugs. Okay, and in this case, linters perform static code analysis. So what you would basically have to do is you would have to input your program or the program that you've written, and then the linter is going to analyze that program statically. That means without executing the code. And based on that static analysis, it's going to throw a bunch of warnings to say, oh, there's a syntax error in this line. Okay. There's a few that are available out there, but two of the most common ones that people use are ESLint and JSLint. So ESLint, this one's implemented as a Node.js application. So there's a little bit of a setup involved, but it's actually a little bit more powerful than JSLint as well, because it supports the creation of custom rules. So maybe there are certain rules that you want to customize. You can create that quite easily using ESLint. And the other option would be using JSLint. This one doesn't require any setup because it's an online tool. But the problem with it is that it's a little bit more limited because it's only tailored towards the JavaScript subclass of the ECMAScript language, whereas ESLint actually supports other subclasses of ECMAScript. Okay. And for this one, you also are not able to customize the rules. There are certain rules that are there, and you can specify exactly which rules you want to use, but you won't be able to create your own custom rules. So let me just demo this one really, really quickly. Okay, so this is JSLint, and let's say that we're using that same function that we had from before, that very simple calculator that only adds function. And you want to check whether your code is fine. All right. In this case, if you click on JSLint, it's going to say that, well, it's going to say nothing because there's actually nothing wrong with the code. But let's say that you're missing a semicolon. So it's going to throw a warning. Despite the fact that semicolon actually isn't required for JavaScript, it's still going to throw a warning because it's a sort of a styling issue in some ways. And we're going to be talking a little bit more about that later on. But let's say that the error in this case is something different. Let's say that you remove this parenthesis. So it's the same thing, right? So it says expected, this closing parenthesis, but instead saw another character. So the point is you basically have this tool that allows you to input your written program, your written JavaScript program, and it analyzes it statically for you, and it tells you where the syntax errors are. Okay. All right. So that's for syntax. So that's for syntax for JavaScript specifically. But there's also linters that are available for HTML and CSS. So for HTML, for example, we can use what's called a validator. So W3, the organization, has a validator that's available up on their website. And there's also this free formatter website that you can use to validate your HTML code. Okay. So this one's not just used for HTML code that you've written yourself. You can also use it for HTML code that's generated automatically by the code. And that's probably the best use case for this, actually. So let's say that you have PHP code that writes HTML or generates HTML. Then in that case, you can grab that HTML code and feed it into any of these two validators. And it's going to show you whether there's any syntax errors. You can do the same thing. Like let's say that your JavaScript code is creating an inner HTML input. So in that case, you can do the exact same thing. You can also feed it into these validators. Okay, and then of course for CSS, there's corresponding tools as well. So there's a CSSLint.net, or if you're in want for something a little bit fancier, you can also use something like StyleLint. Okay. I kind of highlighted this earlier, but linters don't just detect syntax-based bugs. You can also use them to detect any styling issues. And again, it's useful, especially if you're working on a large organization, you have a lot of people working on the same code. You want to make sure that there's a consistent style that you're using in your code, right? So you can specify what those styles are. And if it catches that, oh, this part right here, maybe the indentation is a little bit off, then it's going to throw a warning saying that it doesn't follow the style. Okay. So a couple other JS linting tools that are available. And of course, modern IDEs also come equipped with linters, so you can also make use of those. Now on the semantic side, so as I mentioned earlier, when it comes to detection, one of the most common things that we do obviously is testing. So there's different kinds of tests that you can run. You can run unit tests, for example. So similar to those Java and C++ programs, you can test individual components of your code. So that's what unit testing is. Excuse me. So in this case, we're testing the JavaScript code as a standalone entity, kind of divorced from the HTML and the CSS code. So it's useful to do this because you also want to test whether your code, your JavaScript code works, regardless of what input is provided to it. But at the same time, it's also not holistic because obviously, as I mentioned earlier, web applications are polyglots. You know, they're intrinsically tied to different languages. You know, there's different languages interacting with each other. So you need to also take that into account. So in this case, since the JavaScript code is being tested as a standalone entity, that means you need to mock the HTML and CSS objects that are used by your JavaScript code. So a couple of options that you can use for unit testing for JavaScript. So you have Jest, Jasmine, Mocha, and Puppeteer. So these are all very, very common. I think the one that I'm most familiar with is Jasmine, but all of these are used very, very commonly as well in industry. Okay. So apart from unit testing, you also have something like end-to-end testing. So in this case, you want to test not only individual components of the code, but you want to test whether the entire code works, you know, from as a black box, basically. So you're providing an input, you want to make sure that the output is actually correct. Okay. So for traditional programs, you often just need to provide some value, and then you want to check whether the output, which is also a value, is correct. But in this case, since JavaScript is event-driven, you need to sort of emulate those interactions somehow. Okay, and the most popular sort of de facto testing framework that we use in general, not just for our team, but just in general, is called Selenium. It's very useful because you can basically write end-to-end tests in several languages. So you can write it in Java, you can write it in Python, and so on. And you can also do record replay using Selenium. So maybe you want to come up with your own test cases, your own end-to-end test cases. And you don't want to write like all that code. You can just do a recording and then it's going to write the code for you. Okay, so this is one of the options for end-to-end testing. All right, and then the other sort of more research-based option for detection, functional detection, is using static analyzers. So unlike linters, these ones actually try to analyze your code and try to make conclusions about the semantics of the code. Okay, so for linters, it's more about the syntax, but for these static analyzers, it's more about analyzing the code statically to figure out what the semantics are, basically. Okay, so a couple of examples here are two tools that I basically made during my PhD. So you have this Oribesh, which detects inconsistencies in Angular applications, and then Holocron, which detects inconsistency rules within given subclasses. All right, so that's for the detection side. How about for the localization? So how do we localize functional issues? Okay. As we mentioned earlier, we have to be very, very clear about what we mean by root cause here, right? Because root cause is a very vague term. It depends a lot on what level you're performing the localization on, okay? So here there's two different levels that we're going to be considering. We're going to consider the code level, And we're also going to consider the commit level. All right. So for code level, there's a lot of different standard practices that people use. And again, the granularity that you're performing the localization on really depends on your goal. So maybe your goal is to figure out a certain statement. What's the first variable in the JavaScript code that takes on a certain incorrect value? So in that case, the output is probably going to be a statement. Or maybe your goal is figuring out which function has incorrectly constructed inputs passed to it, right? Okay, so your goal is going to be different, or the granularity is going to be different depending on your goal. Okay.
Okay, I found.
Sorry. Yeah, that's a possible issue that you would encounter when your software is correct. Anyways, so what are some standard implementations? So one thing that you can do is you can do console logging. So as I mentioned earlier, you can put in logs in your JavaScript code using the console.log API to figure out whether your code is executing in a specific control flow. Okay. And then, of course, the other option is breakpoint debugging. And then in this case, you can use something like Chrome DevTools. I'm actually going to be doing a little bit of a demo later on this. So just watch out for that. Okay. So I put in this little caveat here. Since web applications are highly multilingual, so they're polyglots, and these standard localization practices are mostly JavaScript based, it's very possible that whatever root cause you localize, it can be far away from the actual fix that you're performing, or that you need to perform. Okay, so once you actually get a localization output from your by applying these standard practices, very often you need to do a little bit more than the output. You need to go beyond the output, basically. Okay. So that's for the standard practices. Another thing that people have done in the past, again mostly relegated to research, is code analysis. So one example is you can do something like backward slicing. So for example, you have this JavaScript line of code here. So you have var elem equals document.getElementById, by and then it's taking on this constructed string as a parameter. So you have muse dash, and then you have the string from category and the string from ID. Okay, so let's say that this line of code returns undefined. Let's say that getElementById returns undefined. In that case, you're probably going to be interested in finding out whether this is incorrect, this use dash part is incorrect, maybe category is incorrect, or maybe ID is incorrect. Okay. And in order for you to do that, one of the things you can do is you can do backward slicing. So that means you're going to be tracking which or where this particular value came from in category. And you would do the same thing for ID. And then you basically just backtrack through your code until you reach the point where the value itself is actually assigned to a certain variable. Okay. So that's for the code level. You can also do localization at the commit level. And one of the neat things that you can actually do is you can do something called bisection. It essentially uses the same idea as binary search. You have a list of commits, and then you need to figure out which commit was the first one to introduce a bug. So for example, here you have 8 different commits. What you can do is you can check out maybe commit number 5, which is right in the middle or somewhere in the middle, and then check whether it's a good build or a bad build. If it's a good build, then that means your search space is going to be decreased to basically this latter half, or this first half rather. But if it's a bad build, then your search space is going to be decreased to this the second half. And then you would just do that recursively until you find the commit or the first bad commit. Okay. This is very useful for web applications because in this case, you're basically considering end-to-end behavior. And it's also used to localize performance issues, not just functional issues, which we're going to be talking a little bit more later. So one little caveat that I need to mention here is that here we're assuming that the commits are sort of structured as an array very neatly. But in reality, they're actually going to be structured more generally as a directed acyclic graph. So it's not going to be quite as neat as this, but the same idea applies basically. So you want to grab the middle commit, where it's defined in a certain way for DAGs, and then you want to decrease your search pace recursively. All right. So the last thing that I want to talk about regarding localization is spectrum-based fault localization. So again, this is more on the researchy side. But the whole idea here is you want to use your unit tests. You want to leverage on your unit tests to perform the localization to figure out the commits or components that are leading to the fault. Okay, this is a very heuristical technique, so it's possible for there to be false positives. All right, and then of course the last one is on repair. So how do we repair functional issues? I would say that in terms of tooling, this is probably the least supported of the three phases. But there's a couple of tools that people have proposed. So one of them is my tool. It's called Vajovis. So this is a technique that basically uses the doctor-patient analogy to fix DOM API parameters that are broken. Okay, so it's very localized towards a very specific type of bug, but it's a repair technique nonetheless. And then another one that's a little bit more general is called genetic repair. So the idea here is you mutate certain portions of the code, and then you analyze the test results to see which lines of code you most likely need to apply the fix to. Okay. Okay, so let's do a little bit of a recap. We've talked about a lot of different things. So we talked about what we mean by debugging in the context of this lecture. So it's the act of detecting, localizing, and repairing functional and non-functional defects in a piece of software. Okay. We also talked about how web applications present unique challenges in debugging because it's polyglot, and there's also a lot of very loose properties that exist in JavaScript. Okay, and then we also went over some of the tools that are available for each of those three phases. So some detection tools, localization tools, and repair tools to facilitate the process of functional debugging. Okay, so the question now is, what about performance bugs? This is what we started with. I mentioned that this is one of my central focus in this talk, even though it's not necessarily what we're talking about the most here in this lecture. But what about performance bugs? Before we go over that, I'm just going to give you guys a little bit of an overview of the stuff that we do in our team at SAP. Okay. So for those of you not aware, SAP is basically an enterprise software company. So what that means is that we mostly sell our products to businesses and other companies. Okay. And that's actually one of the reasons why you probably don't hear about us as much as other companies like Microsoft and Google. Even though we're one of the biggest companies in the world, we sell our products mostly to businesses, not to the general public. Okay. And the specific team that I'm working for in SAP is called the PNR team, or the Performance and Reliability team. So we're a team of right now 12 people, including 2 interns. So we actually hire interns every 4 months or so. There's going to be a new one coming in, I think, in January. And the goal of our team is basically driving all performance-related issues in our product. Whatever performance issues come up, we're the ones who are going to be driving that in some way. Okay. And the product that we're working on is called SAP Analytics Cloud, or SAC. Okay. What does that entail? So that entails monitoring response time-based metrics. So that's what people usually think of when they think of performance, is how fast a certain action occurs. But not only that, we also look at things like memory, CPU usage, and also network-based metrics as well. Okay. And SAP Analytics Cloud in this case is actually a business intelligence and planning platform that's implemented as a really, really huge web application. Okay. So you can think of it kind of like the way that I usually describe it during interviews is it's kind of like Excel on steroids, but it's actually much more than that. Because the Excel part is probably more on the planning side. The BI part, it's more complicated. So you have stuff like charts and different kinds of widgets that allow you to understand the numbers that you're getting in your business. Okay. There's many teams working on this product over the world, all over the world. The biggest group would be in Vancouver, but there's also teams that reside in Germany and India as well, and a bunch of other countries. So in the P&R team, there's actually two different tasks that we perform. The first task, which probably takes up around 15% of what we do, is running and maintaining performance regression tests. Okay, so we basically have test infrastructure. We run them on a daily basis, and we need to check whether there's actually any regressions that have been introduced in the product in terms of performance, that is. Okay. So as I said earlier, a regression is basically a bug that's introduced to the program after subsequent commits. So the feature was working before, but now it's not working. And a performance regression basically means this part of the program was performing okay before, but now it's not performing fine. Okay. And there's different metrics that we use. So we use, as I said, response time, memory usage, CPU utilization, network latency, etc. Okay. Again, this one doesn't take up a lot of our work hours just because of the fact that most of the test infrastructure already exists. So usually it's just a matter of us maintaining it and monitoring the results on a regular basis. And the other activity, which takes up maybe around 85% of what we do, is investigating performance regressions. Okay, so you have these tests right here that are running on a regular basis. We monitor it. And whenever we see any changes in performance, we need to investigate it somehow. We need to figure out exactly where that change is coming from. Okay, so that's where the whole localization aspect comes into our work, right? Okay. And also, as I said here, due to the inherent variance in performance numbers, the root cause doesn't always end up being product related. So maybe you see a performance change in one of the workflows, but it doesn't necessarily mean that the product itself is to blame. It's possible that maybe there's something wrong with the environment, something wrong with the machines that we're using, that kind of thing. Okay. The problem in this case is that performance debugging is not as well supported in terms of tools compared to functional debugging. So that means we need to perform a lot of research to come up with new techniques and new tools to make our job easier for us, basically. Okay. And we also make changes to the SAC code, but most of the actual development and programming that we do goes into these tools that we create and these techniques. All right. So if you notice the way that I described it, this running and maintaining performance regression tests part, this one refers more to the detection side that we talked about before. And this performance regression investigation task pertains more to the localization side of things. So what about repair? In this case, we also play a vital role in performing repair, but it's not quite as direct. So what usually happens is whenever we localize a certain performance change, and then we've determined that it's an actual regression in the product, what we would do is we would file a defect or a bug report to the corresponding team, and then that team is going to be responsible for actually applying the fix. But even though we're not directly responsible for applying the fix, we're still there to drive that whole process forward, basically. So if we have any suggestions on what the fix should be, we would communicate that to the developer. If there are certain things that, both sides don't understand, so maybe the developer doesn't quite understand what's going on, then in that case, there needs to be some sort of discussion that's happening between the developer and our team. Okay. So there's a lot of discussion basically that's going on when it comes to trying to figure out what repair to apply. Okay. So that's our team. So what are some of the challenges that we're currently facing? Well, the first challenge, and this is more of a general challenge, is that if you're working for P&R, you need to have good breadth and depth knowledge in this case. A lot of the times it's kind of localized, because if you're a testing team, for example, typically you only need to have that breadth aspect. You need to understand what the code is doing, generally speaking. You need to understand the specifications, all these different things, but you don't necessarily need to understand and go deep into the actual code level itself when you're doing testing, just only testing. If you're a dev team, usually you would be very, very localized towards your specific component that you're implementing. So you can go deep into that code, but you don't necessarily know what all the other components are, right? Well, you should know, but you don't necessarily have a more detailed understanding of what those components do, okay? But in our team, it's actually a little bit of both, okay? So the first thing that I want to say is that we're actually not a testing team. So we run tests to help us understand the performance of SAC, but the understanding the performance part is actually more important than the running the tests part, okay? The tests that we run, it really just helps us understand the performance more. It's not the main thing that we do, okay? So in this case, we need to have a lot of breadth, obviously, because the performance regression can come from pretty much anywhere, from any component. But at the same time, since a lot of these performance issues could be detected at the code level, we also need to have a very, very good specific understanding of these components, very deep understanding of them, okay? I guess just to give you a little bit of an anecdotal example. So we've actually encountered cases where a very small one-line change in the CSS code ended up causing a performance regression. So that sort of goes to show you, it can pretty much come from anywhere. It's not just, it's not just from JavaScript code. It could come from any of these components, basically. Okay, so that's the first challenge. The second challenge is we also need to define what a performance regression is. So it's another one of those vague terms that we're using, right? So we have debugging before, we have root cause before, and then now we have performance regression. So it's another vague term that we kind of have to define. Okay. For functional regressions, it's very simple. So you basically have a web application that's behaving correctly before, and then the dev pushes a commit, and then now it behaves incorrectly. So this is considered a regression because you have this basically workflow right here. So before it was working correctly, and now it's working incorrectly after a certain commit. Okay, so it seems very, very simple, and you would think that this is something that we can apply to performance regressions as well, but that's not necessarily the case, unfortunately. Okay, so first of all, when it comes to correctness, it's not quite as clear-cut for performance regressions in comparison to functional regressions. So for performance regressions, you have a very specific oracle or a set of specifications that you can use. So you know whether a certain commit is good or bad, depending on that specification. But for performance regressions, we don't have an oracle. Just to hammer home this point a little bit further, let's go through this example right here. So let's say that you have a logon response time that used to be 2 seconds, and then after a bunch of commits, it ends up becoming 2.2 seconds. So would you consider this as a performance regression or not? And I'll give you guys 15 seconds to think about this. So is this a performance regression, going from 2 seconds to 2.2 seconds? Okay. So in this case, again, the answer is not very clear cut, right? So you don't have a lot of information here. Just because it increased by 200 milliseconds doesn't necessarily mean that it's a regression. One solution that you might propose is you can set a threshold. So maybe if the threshold is 200 milliseconds, then in that case, you would consider this as a performance regression. But what if you're running your tests and the median increase happens to be 199 milliseconds as opposed to 200 milliseconds? Would you still consider that as a performance regression just because of that 1 second difference? So, it's kind of iffy in that case, basically. There's also this aspect of the behavior of the program, right? So as I mentioned earlier, for functional bugs, the results are often binary. So it's either correct or it's not correct. Either a certain value is output, a certain expected value is output, or it's not output. But for performance, there's actually a lot of variance in the performance numbers. So you won't necessarily get the exact same number each time you run a performance test, similar to what you would get for functional tests, right? So because of that inherent variance and inherent non-determinism, it's very, very hard to sort of make that assessment, right? Okay. So as I said here, performance change in one machine doesn't necessarily guarantee that you're going to see the exact same change in another machine. Yeah. And it's not just machines, but it's also across different types of hardware or even, different types of environments. Okay. And then the last aspect of this is the commit aspect. So let's say that you're performing the localization and then you've made the assessment that yes, based on my own criteria, this is a performance regression. But the next question is it a justified regression? Is it something that actually maybe there's a feature that the developer wants to add? That's the reason why he pushed this commit, and it just so happens that it introduces a regression. So you have to ask, is it justified? Is there something else the dev could have done so that this regression wouldn't exist in there? Or maybe it's something that's completely necessary, right? Okay. So for functional defects, you don't have to ask this question because it's just a simple matter of does it follow the specs or does it not? But for performance, it's very, very important to ask this additional question. Okay. So I guess in terms of like defining performance regressions and what a performance regression is, the answer is yes, of course, we can define what a performance regression is. But because of those factors that I mentioned, we need to make this definition very, very loose. Okay. And the decision on whether something is a performance regression or not, it's very situational. So it really depends a lot on the specific change in performance that you're observing. And a lot of the times it's an amalgamation of experience or precedence, discussions with the developers, and understanding customer feedback. Okay. With that said, we do establish certain rules of thumb based on experience. So for example, if a regression is less than 100 milliseconds, most of the times we won't even bother investigating that performance change because it's very minimal to begin with. Okay, so another challenge would be on the side of detection, basically. Okay, so we want to make sure that our execution environment is as stable as possible because we want to make sure that the results themselves are also stable. Just to give you sort of a sense of how impactful unstable results are. So what usually happens is for each performance change that we observe, as I said earlier, we need to, well, first of all, we need to do a sanity check to see whether, we think it's an actual performance regression. And if that sanity check passes, then we need to file an investigation. And a lot of the times we have to err on the side of caution, right? Because let's say that you're seeing a 1 second change in performance and you don't exactly know whether this is something that I can trust, this is a number that I can trust, you have to err on the side of caution because what if it actually is a regression, okay? The problem is these investigations usually take at least 1 day to finish and usually even longer than 1 day. So what happens is that if your results are super, super unstable, you're going to have a lot of false positives. And each of those false positives would basically cost you at least 1 day for each developer. So it's very, very costly to have these unstable results. Okay. So what are some of the things we do to mitigate this? Well, the first thing is we need to have a clear record of the execution environment. So you need to record, what version of the product you're using, what version of Chrome is running the product. You need to monitor certain resource usages in your environment. So, what's the memory, what's the CPU, because those would also affect the response time, right? Okay. We also need to do some post-checking for the results to see whether they're actually reasonable. And in this case, we use a lot of statistical analyses, basically. So we use t-test, Levine test, modality testing, all these different things. Okay. This is actually an active research area for us. There's a lot of different things that we can do to interpret the results, but the thing is, there's a lot of data, right? So we need to make sure that we, come up with a way to understand and interpret this data as much as we can. Okay. Well, the good news in terms of testing, though, is that it's fairly well supported when it comes to tooling. So you have Selenium, which I mentioned earlier. This is something that's also used for performance regression testing. And you also have JMeter. If you want to do back-end testing, this is what you would use. And Jenkins is sort of the framework that we use to run our tests, essentially. Okay. So another detection woe is not just making sure that the results are stable, but also finding a way to prioritize these performance changes. The thing is, you're going to have all these different performance changes. You kind of have to prioritize which ones you're going to be looking into. And you also need to prioritize specifically which components you want to look into or you want to test in your product. Because SAC is a very, very huge application. And it's completely unrealistic if you just want to test everything. That's not something that's going to work. So you got to make sure that you have sort of this prioritization scheme to help you understand, oh, this is the part of the product that I want to test. Okay. Yeah, I mean, this is a classic problem. It's not something that's local to web applications or even to just our product. It's something that people face on a daily basis, developers face on a daily basis. It's called test case prioritization. Okay. And for us, we mitigate this by focusing on specific workflows that customers have complained about in the past, or maybe those that are historically tied to bad performance. So we obviously want to focus on those and look for ways to improve by testing them and then monitoring how they improve over time. All right, so that's for detection. What about localization, right? The biggest problem with localization is that there's just a huge lack in terms of tools, tool support. Okay, it's not something that I mean, it's a common task. It's something that people do in other teams as well. But just in terms of the tooling itself, there's not a lot that are available, at least for our specific purposes. So that's the reason why we actually spend most of our time doing our research on this specific area. We want to look for ways to improve this tooling, basically. Okay. The good news is that there are some very basic tools that do exist out there that we use. One of them is Chrome Dev Tools, for example. Okay. Not sure if there's enough time for a demo. Okay. Maybe I'll show you guys very quickly. Okay, so what I'm going to do right now is I'm going to use Chrome Dev Tools to record a timeline of the JavaScript execution. So what you would have to do is you basically just need to open Chrome Dev Tools by pressing F12, and then go to the Performance tab. And then you just need to press on Record. And then once you press Record, you need to perform whatever action you want to get the execution call stack for. So let's do that. So now it's recording and it's loading the page, and now it's finished loading. So let's stop the recording. It's taking a little bit of time in this case. Yeah, so in this particular case, I didn't specify it earlier, but basically what I was recording was the ECA website loading, essentially. It's very simple. Okay, so now you have the execution timeline. So this shows you all the functions that executed during that whole time span that we were recording. So you can see that there's all these different function calls that were made. So for example, you have the ready function being called. Each function is called by ready, and then each calls an anonymous function. So this is what I was talking about earlier. You know, for regular call stacks, you would typically just have named functions, and it's very easy for you to sort of map this into the actual code itself. But in this case, it's a little bit more complicated because you have these anonymous functions, and there's no simple mapping, basically. Okay, and then you can also look at other stuff in here. So you'll notice it actually tells you specifically, oh, this one took 9,375 milliseconds, so around 9 seconds basically for this entire operation. And then you can also do the same thing for individual function calls. Okay, so very simple, something very useful, and something that we use extensively in our work. All right, so that's for Chrome DevTools. The problem with Chrome DevTools, though, is that imagine having to do a localization for this using Chrome, using the performance, the timelines that we took. So what you would typically have to do is you need to take the timelines for 2 versions of the product. So one for the good build and one for the bad build. And you essentially need to do a spot the difference type of comparison between those two. And to make matters worse, because of the inherent variance in performance numbers, you typically have to do multiple comparisons. So you need to have multiple pairs and you need to compare each of those pairs, basically. It's super, super tedious because, you know, this is huge, right? So it's very hard to just eyeball this, basically. Okay. The good news is that in the course of our research, we were able to come up with a tool that actually performs this comparison automatically. So all you need to do is you need to grab these timelines, these execution call stacks, and then you feed it into our tool, and it's going to be able to give you a suggestion on which functions or lowest level functions regressed. Okay. Obviously, there are certain caveats associated with the tool, which I'm not going to go over here, but it's much better than having to do a manual comparison. Okay. Another thing you can do for localization is you can also do the bisection. So we talked a little bit about this earlier in the context of functional debugging, but you can do the same thing for performance debugging. The difference in this case, of course, is that it's much more nuanced, you know. So you have stuff like behavior and the correctness. Again, as I mentioned earlier, these words are not very well defined in terms of performance bugs. So we actually need to come up with something a little bit more elaborate when we're performing this for performance localization. All right, and then another area of interest would be something like machine learning. It's something that we haven't really touched upon a whole lot in our team, but we're slowly getting into this this space as well. Okay. Yeah, the thing is, when you're localizing performance changes, you're essentially doing a classification problem because you need to figure out, oh, is this a back-end issue? Is this a front-end issue? So you have to sort of classify it based on those. Okay, so just to summarize what we talked about. So we talked about debugging as the act of detecting, localizing, and repairing functional and non-functional defects in software. We talked about web applications presenting unique challenges in debugging, both from a functional side and performance side. And then we also talked about certain tools that you can use to facilitate functional debugging, but also tools that you can use to facilitate performance debugging as well, and some of the unique challenges that performance debugging itself presents as opposed to just functional debugging. Okay. All right, so yeah, unfortunately for this lecture, you know, you guys don't have the opportunity to ask me questions live, but you can always reach out. My email is right here. You can either reach me in my main email from SAP, or you can also reach my secondary email. I also have a website that I try to keep up to date. So if you're interested in any of the research that I conduct, You guys can go to this website and download some of the papers that I've written. And then last thing is, as I said earlier, we hire interns every 4 months. So I urge you guys to consider applying to SAP, especially particularly to our team. Yeah. Thanks everyone, and have a good day.